So chapter 9, reactions of alcohols. Okay. And also talks about ethers in this chapter. So to begin, I usually like to review a little bit from chapter 8. I don't know if you both were here on Monday when we talked about this. So alcohols are amphoteric, which means they can be ionized, or they can act as acids and bases, which means they can be ionized in two ways, so have two different charges. So you can deprotonate, remove a proton from the alcohol group, and this forms an alkoxide ion. Okay? That's definitely a term you should know and be able to recognize that as the negative form of an alcohol. You can also protonate it, which means you add another hydrogen, which gives an overall positive charge. This is referred to as the alkyl oxonium. Okay, so alkyl oxonium is the positive form, alkoxide is negative. The reason I go over this is the first couple sections talk about forming these ions or using these ions. So it's important to remember where they come from. So you can actually form alkoxide ions. In chapter 8, they talk about reacting with a strong base. So take an alcohol, react with a strong base, you get an alkoxide ion. You can also react it with what are called alkali metals. If you can picture the periodic table, alkali metals are the very first column, so lithium, sodium, potassium. The important thing to know about this process happens faster the less substituted the alcohol is. So what do I mean by that? So here we have methanol, just one carbon, so no carbons attached to it. Here we have a tertiary alcohol. The less carbon groups you have, the more quickly the alcohol will react, and the more quickly you'll form your alkoxide ion. Okay? This has to do with steric hindrance. So, for example, he could say, when reacting an alcohol with an alkali metal, an alkoxide ion forms. He could say, which type of alcohol would react the fastest, primary, secondary, or tertiary. So you would want the least substituted, which would be primary. Okay? If he puts methanol, that's even less substituted than primary. It just depends on how he words the question and what answers he gives you. Okay? Mm-hmm. Does that concept kind of make sense?
Yeah.
Great. Okay. For alkyloxonium ions, this chapter just kind of introduces you to the concept of this as a leaving group. So when we talk about chapter 6 and 7, so that's Sn1, Sn2, we talk about leaving groups. And you know that the best leaving group is iodine, right? This chapter talks about how an alkyloxonium ion, this H2O group, is actually a pretty good leaving group. This is not a good leaving group. So if you wanted to, for example, run an Sn1 reaction, okay, you would need the leaving group to fall off to form your carbocation. That wouldn't really happen if you have an alcohol. So the first step is actually turning it into this ion, so that way it can readily fall off and you can go through your reaction. I don't think you need to really know many more specifics. It's more about relating it to what you already know from chapter 6 and 7. So in chapter 6 and 7, we talk about alkyl halides. Right? A primary alkyl halide is best for Sn2. A tertiary alkyl halide is best for Sn1, right? The same applies for alkyloxonium ions. So if you have a primary alkyloxonium ion, that's going to prefer an Sn2. So it's the same concept, you're just not talking about an alkyl halide anymore. Okay? Mm-hmm. Great. There are 3 reactions in particular that I think that you should know. So there's esterification, Williamson ether synthesis, and then there's also a related one called intramolecular Williamson ether synthesis. So esterification, you may have gone over this in general chemistry, okay? So this is actually making esters. So what you should know is that you react a carboxylic acid and an alcohol to make an ester. I don't think you have to worry too much about identifying esters. That will come in Orgo 2. But I would know that these are the reactants that are used. Okay. For Williamson ether synthesis, you react an alkoxide ion with a haloalkane. The notes specify primary haloalkane, so I'm going to write that. Depending on how you ask the question, I don't know. I think he would at least give you partial credit, even if you wrote haloalkane. But I am going to just follow what the notes say. Okay. You already know what the final product is, right? Williamson ether synthesis. What does an ether look like? What's the functional group of an ether?
Is it attached to 2 carbons?
Exactly, very good. So you have carbon group, oxygen, carbon group. Perfect. The other detail you should know from this is an Sn2 reaction. Now, really the main difference, so we're still making a type of ether, but we're actually making a cyclic ether when we do intramolecular. So something like this. Okay? Now, I'm just because it's intramolecular, intra means within. So instead of reacting 2 different molecules together, you actually have what's referred to as a halo alcohol. I'll just draw an example just so you can see it. Okay, so a halo, halogen, alcohol, alcohol group. So we have both of the functional groups on the same molecule. So this is actually going to react with this and form your cyclic molecule. So intramolecular, you're taking a halo alcohol, it's closing its ring structure and creating a cyclic ether. Any questions about the differences between normal Williamson ether and intramolecular Williamson ether? Okay. Okay. So really the only thing there's a couple things left, I suppose. So we have naming ethers, some terminology you should know. And hydride versus alkyl shifts. Okay, so for naming ethers, let's just go through a couple of examples. Would somebody know how to name this ether? Okay, that's fine. So ethers, I think there are less steps in naming ethers than there are in other ones. And that's because you use common names, so you don't have to worry about IUPAC naming here. So essentially, you just focus on the carbon groups on either side. So when you have a carbon coming off of your main carbon chain, okay, you name it as an alkyl group. Okay, so what's the prefix for one carbon? Meth. Perfect. So meth is the prefix. When you're talking about alkyl groups, you add that YL, so methyl. So we have methyl and another methyl. So essentially you list out your attachments on both sides and you end in ether. If you have two of the same, you just put di. So di, methyl, ether. Make sense? Okay. So that's when you have two of the same. Here we have two different ones. So we have methyl again. What would we name this one? There's two carbons. Ethyl. Now, would we do methyl ethyl ether or ethyl methyl ether?
Ethyl methyl.
Why?
Because you do the alphabetic.
Perfect. So ethyl, methyl, ether. What about this one? So we have another methyl group. What about this one? 3 carbons, propyl. What would the final name be?
Propyl or methyl propyl.
Methyl propyl. I have to go through the alphabet. Does that make sense?
Yeah.
Okay. Let's do, you could also see cyclic ethers. Again, not as many steps as you would expect. Okay. So this is an example I showed before. So when you're naming cyclic ethers, you start by naming the cycloalkane name. So if we didn't have an oxygen here, if it was just a triangle, what would be the name of that molecule?
Cyclopropane.
Cyclopropane, good. With cyclic ethers, all you do is add oxa in front of it. So this is oxacyclopropane. Any questions on naming ethers? Okay. So some terminology you should know. Sorry for the squeaky marker. So we've got crown ethers, cryptans, and protecting groups. think that's it, yeah. So these really do go together. If you have Dr. Cosper's notes, this is actually 9-5. It's on page 3 of. It's on page 3 of that chapter. It might actually be easier to look at hers, but I will attempt a drawing. Something along those lines. And then at each of these corners. So this is kind of a really bad drawing of a crown ether. So essentially you have a ring of carbons, and you can see there's ether groups, several ether groups all the way around. Now the orientation of these is really important. You can kind of see that all of the oxygens are facing towards the center, which means you kind of have these electrons all in one area, okay? And positive ions are attracted to those electrons. They like being in there. The outside, however, is all just carbons and hydrogens. So the outside is very nonpolar. This is important. So crown ethers and cryptans can both, they're both soluble in nonpolar substances. Polar ions don't typically dissolve in nonpolar substances, but by using these crown ethers, they can dissolve into a substance, into a nonpolar solution. These are referred to as ion transport agents. Because they can move these ions, and again, the main takeaway is that they dissolve in nonpolar substances, but they can transport them as well. A kind of larger umbrella term that you should know is ionophores. Okay, so one type of ionophores are ion transport agents, which include both of these. The main difference between crown ethers and cryptans, crown ethers, think of a crown. Okay, it's just a ring, whereas cryptans, think more three-dimensional, so it's a sphere. So it would basically be like you'd have multiple layers in a more three-dimensional shape. So crown ethers, two-dimensional, just a ring. Cryptans, think 3D, like a ball almost. Okay. Now, protecting groups. Dr. Cosper's notes gives a good example of like a chemical use of protecting groups, but I'm pretty certain like on your quiz, and typically when he asks questions, he uses more of a real world analogy than really talking about chemistry. Like I think he might have used something along the lines of like bodyguards or like the mafia. So essentially protecting groups, you can add them to a functional group. I'll try and use Dr. Cosper's example. So I'm going to use an OH group as an example. So say you have an alcohol, and you want to keep the alcohol, but you want to change something to the rest of the molecule. Okay, but you don't want to accidentally lose your alcohol functional group. You can add a protecting group, which is kind of just like a little shield, if you will, that keeps other molecules from reacting with it. You can then do whatever you need to change the rest of your molecule, whether that's adding more carbons or adding a different functional group, and then you can just remove the protecting group. The only specific example chemically is that alcohols use ethers as a protecting group, but I've never, historically, that doesn't really seem to be the question that he asks. He just wants you to know that protecting groups protect functional groups. And he may, again, use some type of like bodyguard analogy when asking the question. Most students have no problem with the concept, it's just the way that he words it. It might be difficult to tell what he's actually asking you, but don't get sidetracked. All set with this?
Yeah.
Okay. Hydride and alkyl shifts. Okay. And this actually touches a little bit on carbocations, so this will work nicely. Okay. Let's just do a little bit on carbocations first. So it's important to understand stability, relative stability. So if you have primary, secondary, tertiary, you should understand that tertiary is considered the most stable, meaning primary is the least stable. Okay. Now, one thing that's actually pretty cool though, if a molecule forms something other than a tertiary carbocation, you can actually rearrange the molecule to make something more stable. So, let's just say that we form this carbocation, okay? Let's first classify it. Would this be considered a primary, secondary, or tertiary carbocation?
Which one?
This one, sorry. Primary, secondary, or tertiary?
Secondary.
Secondary. So we have one carbon here, one carbon there. So this is a secondary carbocation, okay? So ideally we would want a tertiary carbocation. So you can perform what's called a hydride shift, which just means you switch places between the positive charge and one of the hydrogens right next door. So we could either switch with this hydrogen or this hydrogen. So if we were to switch with this hydrogen, what would this be classified as? Primary, secondary, or tertiary?
Primary.
Primary. So we know that primary is the least stable. So that actually really wouldn't happen. What if we switched with this hydrogen? Primary, secondary, or tertiary?
Which one?
Sorry, where the positive is.
Secondary. Right?
Careful. 1, 2, 3.
Oh, yeah.
So now we have our tertiary. So by performing a hydride shift here, we went from having a secondary carbocation to a tertiary carbocation. So in terms of what to expect, he could do exactly what I just did, draw an example molecule, and just say, using an arrow, indicate which hydride shift would give you the most stable carbocation. So in that, you're just looking for the carbon that's going to give you a tertiary, so something that's attached to 3 other carbons. You can also do what's called an alkyl shift. So let me... So if you were, again, given something like this, okay? So again, we're starting with something that's secondary, but if we switch places between the methyl group and the positive, we again have our tertiary. So you can switch places with a hydrogen or switch places with a methyl group, okay? Both are allowed. And again, you're just looking for the carbon that's attached to 3 other carbons.
So you just want to put the positive charge on the tertiary carbon?
Exactly.
Okay.
You got it. That's essentially chapter 9. Were there any topics that I might have breezed over that you can think of, or? I know you wanted to talk more about carbocations, so we could definitely need to talk more about those. That's not.
Okay.
Let's go with that. So other than knowing, with carbocations, there's really two sides of the coin you need to understand. So the energy it takes to form the carbocation and the stability of the carbocation once it's formed, okay? So again, we have methyl, primary, secondary, and tertiary, okay? So stability, we know that tertiary is considered the most stable. So as we move closer to tertiary, we become more and more stable. The energy it takes to form is indirectly related. Meaning that a methyl or a primary carbocation is going to take the most energy to form. Okay? They really feed into each other. So if, essentially you can think of it as the molecules don't want to waste time and energy into making something that's going to be very unstable. So if we know that a primary carbocation is going to be very unstable, that just means it takes a lot of energy to get it into that very unstable state. So that's why a tertiary carbocation is both the most stable, takes the least energy to form and is also the most stable. So this is the same for radicals. Should probably radicals and cations, but this is more so related to radicals. Trying to think if there was anything else. You're going to probably see a lot of questions on stability. Was there anything else specifically with carbocations that you wanted, or was this?
Basically that. So like, I was gonna ask like, which molecule is most stable, right?
Yeah. So something like he could directly ask you which carbocation, which radical is most stable. He could also expect you to know that to answer other questions. So this comes into play when we talk about like Sn1 reactions, because Sn1 makes a carbocation intermediate, so you need to know which one is the most stable. So even though he's not asking you directly, you need to use that information to answer a question about that equation. Okay? Moving on to Syn versus Ante.
Yeah. Could we go over the Sn1 and 2?
Yeah,
later?
absolutely.
Okay.
That's usually, is that a chapter you were interested in? Yeah. It's usually a pretty confusing one.
Yeah.
Okay. Just so I don't forget. Okay. Okay, so Syn versus Ante Addition. These are just vocab terms that you should know. So more generally, when we're talking about addition reactions, you are starting with an alkene. You're going to break the pi bond but leave the sigma bond. And you're going to add something to both carbons. That's where the addition comes from. Syn and Ante just refer to how those are added. So with Syn, it actually is going to look exactly like what I just drew. So both substituents are added to the same side of the carbon. With Ante, as the name kind of lends itself to, you have additions happening on opposite sides.
That makes a lot more sense.
Yeah. You will see, like in chapter 12, chapter 13, they use these terms when discussing certain reactions. Those are definitely details I would recommend, taking note of. So for example, like in hydrogenation, hydrogenation is a type of addition where you add 2 hydrogens, and that is an example of Sn addition. So that's a detail you would want to know about that reaction.
What's the difference between Markovnikov?
And anti-Markovnikov?
Yeah.
Okay.
Wait, no. Wouldn't it be the same thing as that? Like, same basic structure?
I wish it was that easy. It has to do with, so it's a specific type. It doesn't have to do with same side versus opposite side. It's when you're reacting like hydrogen and something else. So it could be hydrogen and a halogen. It could be hydrogen and a hydroxyl group. Essentially, Markovnikov and anti-Markovnikov dictate where the hydrogen goes. So as an example, if we did okay, so Markovnikov, the hydrogen is going to go to the least substituted carbon. Okay, anti is just the opposite. So most substituted. So if we use this as an example, we're going to break our bond. Okay, so if we were doing Markovnikov, okay, the hydrogen is going to go to the least substituted carbon. So if we had to choose between this one and this one, would this be considered primary, secondary, or tertiary?
Primary?
Okay. This one?
Tertiary.
Tertiary. So this is the most substituted, this is the least substituted. So Markovnikov would mean the H goes here, and the other attachment goes here.
Okay.
Okay.
And that other attachment is what?
So typically it's either going to be a halogen, so fluorine, bromine, chlorine, iodine, but you can also see it when you are doing hydration. So H2O breaks up into our hydrogen and our OH group. So that would also follow Markovnikov, anti-Markovnikov.
So would it be instead of that methyl right there? The
Sorry.
CH3?
So this, I've just drawn it a little bit differently, but these CH3s are here and here.
Okay.
Yeah, sorry, it's not very nicely drawn. We could do it like this.
Oh, okay.
Yeah, sorry. Is that a little bit clearer?
I was just wondering where.
Yeah,
coming
that
from.
I see that. That looks a little weirder now. Okay. So yes, Markovnikov, all it's dictating is where the hydrogen is going versus the other. Again, this is another detail you'll see. One shortcut. If you see electrophilic, that's an indicator that it's going to be Markovnikov. So there's electrophilic halogenation, electrophilic hydration. If you see radical, that's an indication that it's going to be anti-Markovnikov. So that won't give you the answer for all of them, but at least that's one shortcut for like 4 of them.
That makes more sense.
Okay, good. The next thing on the list is thermodynamics and kinetics. Are we good to move on to that? Okay. Let's first just talk about kinetics, just because there's not as many details, and this one you students are usually more familiar with. So kinetics think movement, right? So kinetics just refers to the rate or speed of a reaction. Okay? When you're running a reaction, this is an example of one way that it might, like one picture of a reaction. So here you have your reactants, your products. Oops. You see this hump here, okay? This hump is important. It's referred to as activation energy, or the energy of activation. This is the amount of energy that needs to be produced to kind of get the reaction started. At the top, you form a transition state. So you need that kind of boost of energy, you make your transition state, and then the reaction can take place. The real important detail that he wants you to know from this chapter is the role of a catalyst in all of this. So catalysts speed up reactions, right? Do you guys remember how they do that?
Lower activation energy.
Perfect. So they make it so there's less energy to kind of get everything going, so the reaction takes much less time to happen. That's really all you should worry about for kinetics, okay? Thermodynamics, there are really two concepts to know. So the first one is the Gibbs free energy equation. He's been pretty clear that he's not going to expect you to do any math with this, but you should understand each variable and how it applies to thermodynamics. Actually, what is thermodynamics?
The ability for something to happen.
Good. So another way to think it, the extent to which a reaction will take place. So is it favorable or is it unfavorable? Okay. So delta G is just your Gibbs free energy. It can be either positive or negative. Which would be considered a favorable value?
Negative.
Negative. So if you have a negative delta G, that indicates a favorable or spontaneous reaction. It's going to react on its own. You don't have to provide any additional support. So that would mean a positive delta G is going to be an unfavorable reaction. What does delta H stand for?
The entropy? Or
Close.
Enthalpy.
Enthalpy. Delta S is entropy. The way I like to remember that is there's an H in enthalpy.
Yeah.
Okay. Enthalpy can be calculated, and does anybody remember how? How do you determine delta H?
Bonds broken, minus bonds formed.
Very good. So the amount of energy it takes to break those bonds minus the amount of energy to form the new bonds. A good way of remembering the order is that they actually go in alphabetical order, which is nice. What value for delta H indicates a favorable reaction?
It'd have to be negative.
It is negative.
Yeah.
Okay, so you can kind of keep delta H and delta G in the same place in your mind. So a negative delta H is favorable, positive is unfavorable. Delta S we said is entropy, but what is entropy?
Disorder.
Good, so the amount of disorder in the reaction. So this is really seen by, so if you started with one molecule and you end with two molecules, you've increased the disorder. You've increased the number of species in an environment. So what value indicates favorable, positive or negative?
Positive.
This is the one that's different. We want more disorder. We prefer disorder. So a negative delta S would be considered unfavorable. You seem to really get this. How are you feeling about this?
I'm okay with this part.
Okay. I haven't gotten to the, okay. Is it the K that throws you off?
Yeah.
Okay, all right. So Gibbs free energy is one end, equilibrium is the other end. So equilibrium is determined by a constant, KEQ. You may also just, he might just write K. You can, we're really just looking at the rate at which A is turned into B and B is turned back into A. So you can find K by taking the concentration of B over the concentration of A. So products always go over reactants. So with this one, K is never going to be negative. It's either going to be less than 1 or greater than 1, but it's not a negative positive game anymore. So K is either less than 1 or greater than 1. If we have something that's less than 1, favorable or unfavorable?
Unfavorable.
Why unfavorable?
Because there's going to be more reactants and products.
Very good. So if we have a value that's less than 1, that means we have a much bigger value on the bottom, which is not a favorable scenario. You'd rather be making product than taking in product and making your reactants again. So unfavorable. So on the flip side, a larger K is considered more favorable. The bigger the K, the better. Does that make sense? Okay. So usually gives you a very exaggerated number, so either K equals 1,000,000 or K equals 0.00001. So it's typically not very close to 1 at all. So as long as you remember this, you should be able to answer any of those types of questions. All set with thermodynamics and kinetics? Okay, I have a question for you guys. If you have an unfavorable reaction and you add a catalyst, will that increase the rate, decrease the rate, or cause no change?
Would it do anything?
Okay, so wouldn't do anything. What do you think?
Speed it up.
So speed it up. That's kind of the jerk reaction, right? Because we know that catalysts speed up reactions. The key with this is you have to keep these mutually exclusive. Catalysts will only affect the rate if the reaction actually takes place, right? So if you have an unfavorable reaction, a catalyst isn't going to suddenly make it favorable, okay? It's like adding gas to a car that has a dead battery, okay? It's not going to make it go any faster. It's not going to make it start, okay? That's a trick question that comes up a lot, so I'd be prepared for that. Okay, chapter 6 and 7 now. Okay. So I would recommend being comfortable with the chart that Dr. Cosper and I think Dr. Fred included it in his notes. I did make a slight change just due to some information in the textbook, which the chart doesn't really talk about. So it's slightly more complicated, but a lot of the concepts are still the same. the other piece together. Okay. So essentially what I've done is I made another row, and I have E2 in two different places. So I just want to briefly touch on why I've done that. So in Dr. Cosper's notes, you basically just have Sn2 E2, Sn1 E1. Unfortunately, E2 reactions, when we're talking about primary alkyl halides, really only occur if you have a very bulky and strong nucleophile. More of the time, you have secondary or tertiary reacting in an E2, okay? So there are some situations where this will happen with primary, but most of the time it happens with secondary or tertiary. So I just want to try and make that a little bit more clear. So let's go through each of these and just talk about the components and why they are the way that they are. So with Sn2, what does Sn2 stand for?
Substitution nucleophilic will die, right?
No, so you got it's bimolecular. So substitution, nucleophilic, bimolecular. The bimolecular refers to the fact that the rate of that reaction is affected by the concentration of two reactants. So if we change either the amount of the alkyl halide or the amount of the nucleophile, that's going to affect the reaction rate. Okay, so bimolecular reaction rate is affected by two. So the very first thing that we see is that Sn2 reactions prefer primary alkyl halides. And a lot of this has to do with where the attack is taking place. So if we if this is, our nucleophile and our alkyl halide, this nucleophile is trying to attack the center carbon specifically. It's not going to try to attack anywhere else. So this type of reaction prefers primary because if we had big bulky alkyl groups, like in a tertiary alkyl halide, the nucleophile would have a really hard time getting through that. Okay? So another word for that is that it reduces steric hindrance, okay?
What does?
Having only a primary instead of a tertiary.
Okay.
So the fewer bulky groups you have, the less steric hindrance you have. So this also goes along with why we want a small nucleophile. Because we have to get in and attack this center carbon, we can't have a big bulky nucleophile. It's just not going to work. So this reasoning applies to this as well. So we want a small nucleophile and a primary alkyl halide, so we're reducing steric hindrance as much as possible. Okay? You'll notice that I drew an arrow. I drew it in a very specific way. So there's two different things to see here. The fact that I only drew one arrow, okay? I drew one arrow because the carbon can only be attacked at one certain angle, okay? And that's a very specific place. So this is referred to as nobody else is down here, Alex.
I was looking for Abby.
Oh, no, I haven't seen anybody.
Okay.
This is referred to as being stereospecific. So the reaction can only occur at this point on the carbon. This is referred to as a backside attack because it's on the backside of where the halogen is located. So Sn2, you should remember backside. Okay. Once the nucleophile and the alkyl halide collide, you get this type of structure happening. So the nucleophile and the halogen are kind of bonded at the same time. This happens when you have what's called a concerted reaction. So bonds are being broken and formed at the same moment, which create what we call a transition state. So this is our transition state. The other detail you have to know has to do with the type of solution that this is taking place in, so the type of solvent. SN2 reactions prefer polar aprotic solvents. What does the term aprotic mean? Something about protons. What does A typically refer to?
It doesn't have protons to give.
Exactly. So it doesn't give off protons. Another way of thinking about it is it doesn't give off H plus ions. So let's talk about why. So if we had a bunch of H plus ions floating around, is there anything in the reactants that might react with that H plus? We've got a negative nucleophile, right? So these protons can tie up your nucleophile. So that's why we don't want polar aprotic. So doesn't tie up nucleophile. That's really important because this is a bimolecular reaction. So if some of the nucleophile gets used up reacting with the protons, we lower that concentration, we're going to slow down the entire reaction. Okay? So we don't want protons floating around, we don't want to tie up the nucleophile and slow everything down. Okay. So after the transition state forms, you end up with our nucleophile substituted for where their halogen was. There is one other piece, and it has to do with the fact that this is stereospecific. So let's do a quick review of absolute configuration, right? R versus S. So if I asked you to figure out the absolute configuration of this molecule, the first thing you have to do is prioritize the substituents based off of their atomic weight. So which one of these has the highest atomic weight?
C.
This is a tricky one because it's a halogen. So even the smallest halogen, which is fluorine, is technically heavier than carbon. So the halogen, in this case, would be the first one. It's a tricky one. Then the carbon. Hey, Amber. And then we have both hydrogens, so that would be 3 and 4. So this would be R or S? If it's clockwise,
R.
R. If we look at our final product, again, we can assume even the smallest nucleophile is typically going to be heavier than carbon. Then carbon. We went to S, right? That's going to happen in every SN2 reaction. So you're going to go from R to S or S to R. Yes, Amber?
So if you have in an Sn1 reaction,
Yep.
and it's an R isomer, and you do the reaction.
Yep.
It would normally be a racemic mixture, or it would stay R, right?
So as far as I know, it would be a racemic mixture just because in an SN1 you have the two different sites.
But if we
To
were
react.
asked for like the configuration of it,
Interesting. You would keep R,
that's what.
I'm pretty sure.
Yeah, because I have that in my notes. But
Okay.
I wasn't sure.
Yeah, that's a tricky one, but I'm fairly certain. I'd have to double check because that's not in Dr. Cosper's notes, so I'd have to take a look in the textbook, but that's a good question. Okay, so again, SN2 prefers primary and a small nucleophile to reduce steric hindrance. It's stereospecific because it can only perform a backside attack There's only one place to attack. Bonds are broken and formed at the same time, making a transition state. And it prefers polar aprotic solvents so that it doesn't tie up our nucleophile and slow down the reaction. Our final product is just a substitution of the nucleophile, and our configuration is going to switch. Good with Sn2?
Mhm.
Okay. Okay, so moving on to E2, technically again you're going to expect to see either a tertiary or a secondary, but our big difference here between Sn2 and E2 is where the reaction is taking place. So if you remember in Sn2, the nucleophile is attacking that center carbon. It's trying to get in to attack that carbon that's directly bonded to that halogen. With E2 reactions, it's reacting with one of the peripheral hydrogens, okay? Now, it's a very specific hydrogen. It's always going to attack the one that's opposite the halogen. This is referred to as a topside attack. Because it can only attack this one hydrogen, it's still considered stereospecific. Okay. So, again, it's because bonds are broken and formed at the same time, we're going to form a transition state. So in this transition state, the black dotted lines are bonds that are forming, the orange dotted lines are bonds that are being broken. So we have the nucleophile picking off this hydrogen here. So it's going to break away from the carbon. This bond is going to be broken, the halogen is going to break off. That leaves both of these carbons with only 3 bonds. So that's going to drive a carbon-carbon bond to form. Okay? So our final product is an alkene. Elimination reactions make alkenes. Okay? We still want polar aprotic solvents because we don't want to tie up our nucleophile. We now can have big, bulky nucleophiles because we're not worried about attacking the center carbon. We're not worried about steric hindrance. We're just trying to pull off that peripheral hydrogen. So typically secondary, tertiary, big, bulky nucleophiles, all the same information for all the same reasons as Sn2, but we have a different final product. We have an alkene now. And,
so what's the transition state called?
So you don't need to know the specific term. It's
Okay.
just a transition state.
Okay.
So in a concerted reaction, bonds are being broken and formed at the same time, so you form a transition state. Okay. Moving on to Sn1 and E1. Okay. So we know the 2 stands for bimolecular. The 1 now stands for unimolecular. So this means that the reaction rate is only based off of the concentration of one of the reactants. And that's based off of your alkyl halide. So we can take away, we can add nucleophile. the reaction rate isn't going to be changed at all. But if we play around with the amount of this, that's going to affect the reaction rate. So if we increase the amount of alkyl halide, that increases the reaction rate. Decrease concentration, decrease reaction rate. Okay. So Sn1. The biggest difference, or one of the big differences, instead of these being concerted, these are considered stepwise. So there's 2 steps in these reactions. Okay? The first step is the same for both. Okay, so this first step is considered the rate determining step. So the quicker that this step happens, the quicker the reaction of the entire, the rate of the entire reaction goes. So essentially we see the halogen is falling off and we're forming a carbocation, okay? This should hint to you as to why these prefer tertiary. What's the most stable carbocation? Tertiary. So it would make sense that we wouldn't really have primary alkyl halides running in Sn1 because that would make a primary carbocation, which we know is very unstable. Okay? So tertiary, because it's the most stable carbocation. Instead of a transition state, we now have an intermediate because this is a stepwise function, a stepwise reaction. So it's stepwise, and we make a carbocation. So this is the first step for both Sn1 or E1. Okay. For Sn1 specifically, once we form this carbocation, okay, we're going to react with our nucleophile. Again, we are attacking the center carbon. For substitution reactions, you're attacking the center carbon for both instances. So we need a small nucleophile to be able to attack in that area. You'll notice that I drew 2 arrows. So that means the reaction can take place either on top or below. Would this be a stereospecific reaction? No, because there's more than one place. So this is not stereospecific. Now, just by probability rules, essentially half the time the nucleophile would attack from the bottom, the other half it would attack from the top. So you would end up with 50% of each type of enantiomer. When you have equal amounts of 2 enantiomers, you make a racemic mixture. The only other detail you need to know is the type of solvent. So for this type of reaction, they prefer polar protic solvents. So with this one, we don't necessarily care if there are protons around. Technically, we don't care if the nucleophile gets tied up, right? If we use some of our nucleophile, if it reacts with the hydrogen, it doesn't affect the reaction rate because the only thing that affects the reaction rate is how much of this we have. So we don't care if our proton or our nucleophile gets tied up. So Sn1 prefers tertiary alkyl halides because it makes the most stable carbocation. We still need a small nucleophile because we're attacking that center carbon. It is 2 steps, with the first step being the rate determining step. A carbocation intermediate is formed. It's not stereospecific because the nucleophile can attack the top or the bottom of the carbon. It prefers polar protic solvents, and again you end up with a substitution of the nucleophile for the halogen. Yes, Amber?
What's the charge of the carbocation?
What is a cation?
It's plus.
Yes.
So it's just 1 plus?
If you had to quantify it, yes.
Okay.
Okay. Any questions on SN1? Okay. E1, again, this first step is identical, no change there. The only change is we're no longer attacking the center carbon. We're attacking the outside hydrogens, okay? That's the same for these. Center carbon, peripheral hydrogens. Would this reaction be considered stereospecific? No. I've drawn 3 arrows. The nucleophile can react with any of those hydrogens. So again, stability, tertiary stays the same. The only difference between these two, we're changing where we're reacting. We're pulling off one of those outer hydrogens, so we're going to end up with an alkene. Okay?
So elimination always makes alkenes?
Always.
Okay.
That's chapter 6 and 7. How are we doing on time? Wow, we still have a lot of time. Any questions or things that I might have gone over too quickly?
I have one. So, was this question?
Okay.
It said like if you cut in half the concentration of the alkyl halide, so that would like be reducing. So
Which one is it? Sorry, this one.
this one, yeah.
Okay, I'm just going to read it just in
Okay.
case people are watching. You are doing an SN1 reaction and want it to go faster, so you cut in half the concentration of the alkyl halide substrate. Will this speed up the reaction 1, 2, 3, 4 times, or will the reaction slow down, or will there be no change in the reaction rate? So this is an SN1 reaction. They want it to go faster, okay? It is saying that it's, you're taking half, so you're cutting this, the concentration in half. So we know that that's going to affect the rate, but, so you need to know that concentration and rate are directly related. So increasing the concentration increases the rate. They decrease the concentration. So that means the rate's going to go down. Okay? Was there another question from this one, or is that the only one?
Just that one.
Okay. Anything else for 6 and 7? Okay. That was the end of my list. Were there other chapters you wanted to go over? Or were there any quiz questions that you had a hard time understanding the reasoning for? Do you just carry like a bag of snacks around with you at all times?
I have to, I never go home.
That's true. That's fair. Were you guys able to review all of your quizzes in your midterm?
Yeah.
Okay.
Hoffman's postulate.
Oh, what chapter is that from? Chapter
11.
2? Oh, 11.
With electrophilic addition.
Oh, Cytad versus Hoffman, yes.
Did we do that yesterday? I know that. Was that yesterday?
Did we? You did it in the morning? Okay. Yeah, I know. I think it wasn't on the YouTube video because my computer died halfway through. Okay, so these are rules for elimination reactions. Okay, so we're starting with an alkyl halide. We're performing an elimination reaction. We're ending with an alkene. This is indicating where the reaction is going to take place. So we start with this. Okay, so we have our alkyl halide. We know that we're going to make an alkene. To do that, we're going to remove a bromine and a hydrogen. what we need to find out is, are we going to take a hydrogen from this carbon or a hydrogen from this carbon? And that's what Saitev and Hoffman tell us, okay? So with Saitev, you use an unhindered base. I like to think of that as just a small base. And that way you can keep your S's. This is going to attack the most substituted. Most substituted carbon and give you the more of the most stable product. We'll talk about the fact that you end up making both. But so Saitev, small, most substituted, most stable. So let's look at what that would actually give us. So we need to figure out which one of these is most highly substituted. So if we had to classify this carbon as primary, secondary, or tertiary, it would be?
Primary.
Good. And this one would be?
Would that be tertiary or secondary?
Secondary, because we have one carbon here, one carbon
right,
here. So secondary. So we know that this is the most substituted carbon. It's higher substituted. So we're going to take off this bromine and this hydrogen. Okay? This would be our final product. Technically, we make about 70% this. If we were to remove this hydrogen, we'd make this product, and with Saitev's rule, that's going to happen about 30% of the time. So the majority of our product is going to be the more stable product. We will get a little bit of the lesser stable product. Who can tell me why this is considered more stable than this?
The 30% one is terminal.
Very good, yes. So we've got an internal alkene here, which is more stable than a terminal. Okay. So that's Saitev's rule. You're going to use a small base, attack the most substituted carbon, and end up with more of your more stable product. With Hoffman, you have a big bulky base. It's going to attack the least substituted because of steric hindrance. And you're going to get more of the least stable product. So essentially these would be flipped. Okay, it might not be exactly 70-30, but you're going to get more of the terminal alkene and less of the internal. Okay? Probably not going to be drawing related, but he could ask you questions involving these details. Okay? Good topic. That was only 7 minutes.
Can you go over the addition reactions of alkynes?
So is that chapter 13? So one thing to note, the reactions brought up in this chapter are almost identical to the ones in chapter 12. It's just most of the time the reaction happens twice, not just once. So I would definitely review the details from chapter 12, but we can talk about these specifically, of course. So there's really 4 markers. So hydrogenation. You should know that in this we're adding hydrogen, okay? When we're talking about alkenes, all that's happening is you take an alkene, add a hydrogen molecule or an H2 molecule, and you make an alkane. With alkynes, you just have to do that reaction twice. So, start with our alkyne, and we add our H2 molecule. We're going to break a pi bond and add hydrogens to each side. So if we break one of the pi bonds, that leaves us with a double bond. We have hydrogens here, and we add a hydrogen to each one. Okay? Essentially, we do that again, adding another hydrogen molecule. We break the pi bond, leaving just our sigma bond, and we add in another set of hydrogens. The one detail for this one that is different, so in this first step, when you are making cis alkenes, you do use a specific catalyst that I have seen him asked about. So it's referred to as Lyn Lars Catalyst, and that's for cis alkenes. It's just something he may ask you about. I have seen it before. So hydrogenation, alkyne plus hydrogen equals alkene, alkene plus hydrogen equals alkane. With electrophilic addition, again, anytime you see electrophilic, you should already be thinking Markovnikov. So this is dictating where that hydrogen is going, remember. So the hydrogen is going to the least substituted. So again, we have, I'll use this one as an example. So you're adding HX. So this could be hydrobromic acid, HBr, HI, HCl. Again, you're going to break one of your pi bonds, making an alkene. Then you need to figure out which one is the most substituted. Primary, secondary, or tertiary?
Primary.
Okay. Primary, secondary, or tertiary?
Secondary.
So the hydrogen is going to go to the least substituted. Halogen goes to the other one. This occurs again. We break our pi bond. Again, this is going to just cover, run Markovnikov again. The classifications haven't changed. This is still primary, so we're going to add an H here and X here. So you'll notice that we've added halogens to the same carbon. Do either of you remember what vocab term relates to that? Starts with a G. Geminal, very good. So this is a geminal dihaloalkane. Moving on, radical addition. Again, radical, you should already be thinking anti-Markovnikov. So the H is going to the most substituted. This is the one reaction that's mentioned in this chapter that only runs once. So you're not going to have, this 2 times happening type thing going on. I use the same example as above. So this is just going to the opposite. Now the H is going to go to this most substituted carbon, with the halogen being here. You can have either cis or trans in this case. or excuse me, anti or syn, not cis and trans. So this would be an anti addition. We've added to the opposite sides of the carbon, but you could also have it on syn addition. But this is where it stops. It doesn't take another step further, so that's important to know. With electrophilic addition of X2, I do want to make it clear because I've kind of harped on electrophilic is Markovnikov. Markovnikov is indicating where the hydrogen's going to go. If we're adding X2, there's no hydrogen in there to kind of figure it out. So electrophilic addition of this does not go Markovnikov or anti-Markovnikov. So I just want to make that clear because I know that can be confusing. So again, we start with our alkyne and add our X2. Pi bond breaks, giving us an alkene. You'll notice that this is anti-addition. That part you should know. This reaction is going to run again, so we're going to add another anti-addition here, X, X. So our final product, we end up with 4 halogens. Okay, this is referred to as a tetra. Tetra meaning 4, haloalkane. So again, hydrogenation, 2 rounds of adding hydrogen. When you do have cis alkenes, you use a Lyn Lars Catalyst. Your final product is an alkane. Electrophilic addition, 2 rounds of a Markovnikov addition. So alkyne plus HX gives you an alkene. Final product is a geminal dihaloalkane because the halogens are added to the same carbon. Radical addition of HX is 2 rounds of anti-Markovnikov. So we're going to end, 1 round of anti-Markovnikov. Our alkyne is going to be turned into an alkene, and we can have anti-addition or syn addition. Electrophilic addition of X2, 2 rounds of adding an X2 molecule, so that could be, again, any type of halogen. This is an anti-addition. Our final product has 4 halogens, so that's a tetrahaloalkane. Were those the reactions you were looking?
Mm-hmm.
Okay. Coming up on 3:30. Technically available until 4. If you guys don't have any other questions.
Can you do this from chapter 14 too?
14? Okay. So chapter 14 you can kind of split up into 2 topics. So we have the main topic, which is delocalized pi systems. Also electron delocalization. Then you get specifically into conjugated dienes. So we'll kind of cover those things. Delocalized pi systems and electron delocalization are scarier terms than they really are. So electron delocalization just means electron movement. So the electrons aren't really confined to their bonds. They're moving throughout. And this happens when you have overlapping pi orbitals. So this, a good example, so if we have okay, this is kind of another schematic of this. So we have our pi orbitals all on a nice line here. And essentially what this allows for is electrons to kind of move along. You can think of it as like a roadway, okay? So because these electrons are kind of have this road available to them, it provides a lot of stability. They're very, very, very stable. And that's due to resonance. So delocalized pi systems allow for electron movement, which provides stability through resonance. Okay? This happens anytime you have a double bond next to a single bond. Okay? So a good example. Okay? This is referred to as an allelic functional group. Allelic. Okay, so double bond with an adjacent single bond. You can make cations, anions, and radicals from this group. And essentially the charge or the electrons can be written in different places. Probably the most familiar example of this is this molecule here. Are you guys familiar with this? Benzene. It's drawn with a circle in the middle because you have alternating double and single bonds. The reason that you can draw it in this way is because those electrons are constantly moving. The alternating double and single bonds allows for this electron movement, so you see it drawn with a circle. Okay. So this allelic functional group, very highly stable because of electron delocalization. You should know that these perform, especially allelic halides. So if we were to add a halogen there, these perform very fast in Sn1 and Sn2 reactions. So you should kind of link that up with the information we talked about for chapter 6 and 7. So this is kind of that first half, just talking about those concepts. Now, diene is a term you should be familiar with. So if we break that term up, ene is referring to alkene, so carbon-carbon double bond. The di is just referring to the fact that there must be two of them in this molecule. So you can have a couple different types. If the double bonds are right next to each other, this is referred to as a cumulene. If you have one double bond in between them, that's a conjugated diene. We're going to talk more about those. If you have more than one single bond in between, so here we have two single bonds. This is referred to as an isolated diene, or non-conjugated. So there's another single bond in the middle there. Conjugated dienes are the most stable kind. And it's because we have alternating double, single, double bonds. If you have double bonds right next to each other, or if you have an extra single bond in the middle, you don't get this electron delocalization, and it becomes much less stable. Okay. So we're going to talk a bit more about conjugated specifically. So when you make a cation diene, so let's see here. Okay. So if this was our starting, okay, and we just have hydrogens coming off of these. So if this is our conjugated diene, okay, if we react this with an electrophile, we're going to get a carbocation. Now, because the electrons have free movement, the carbocation can show up on this carbon or this carbon, just by the electron shifting one way or the other, okay? When this reaction is taking place, you can either go through what's called kinetic control, or thermodynamic control. When you're going through kinetic control, you have low temps, you have less time, and you're going to end up with a less stable product. That occurs when the positive charge is here. Essentially what ends up happening you end up with something being added to each of these two carbons. So because you've broken this double bond, you've freed up a place here for the bond to take place, and you have a positive charge here that wants to react with something to receive its electrons. This is referred to as a 1-2 addition, because the electrons, if you were to count them, 1, 2, 3, 4, the carbons right next to each other. So the less stable product is referred to as a 1-2 addition. With thermodynamic control, it's the opposite. So you have more heat, more time, and the more stable product. That's going to look like this. Under thermodynamic control, we would end up with an addition happening here, where the double bond is broken, an addition happening here, where that positive charge has shifted to. So instead of a 1,2 addition, we have a 1,4 addition. So 1,4 addition is considered more stable. Why would this final product be considered less stable than this final product?
Alkene.
Exactly. So 1,4 addition, otherwise known as internal alkene. 1,2 addition, terminal. The only other big thing in this chapter is the Diels-Alder reaction. So with that one, you're reacting a diene plus a dienophile, and you're making something that's called a cycloadduct. So when we're talking about a dienophile, you can think of an alkene or an alkyne for this specific reaction. These two are going to combine and they're going to make a ring. Okay? Now, if you pay attention to the electrons, they're going to shift. So this pi bond is going to shift here. This is going to shift to combine these two carbons together. And this one is going to shift to combine these two. So what we end up with so these CH2s are involved here, and then this is the piece from the diene. This is referred to as a cycloadduct, okay? A cyclic product. So Diels-Alder, diene plus dienophile makes a cycloadduct. This is a concerted reaction, and it is stereospecific. Those are really the big topics from chapter 14. We still have 15 minutes left.
I think I'm okay.
Sure? Okay. Thanks for coming, guys. Good luck tomorrow.
Thank you.